Hello, welcome to AQA Physics Paper 2, higher 2018. Okay, so we've got to this part. So calculate the current from the power supply needed to provide a power output of 336 watts. Use the data in figure 13, so you can look back at here. So obviously important bits are the numbers. So coil, primary coil, 640 turns, secondary 4. Power output we're told anyway. PD across coil, secondary 1.7 volts. It's a very dramatic step down transformer. Okay, so let's write an equation. So number of turns primary over number of turns secondary equals voltage primary over voltage secondary. Okay. So we've got 640 divided by 4, so that's quite dramatic. We don't know V primary over 1.75. Yeah, let's rearrange that. VP equals 640 times 1.75. Okay, then divide that by 4. And then VP equals 280 volts. Okay, now that's a voltage. I want the power. P equals IV, P times V. So we know the power is 336 watts. Is 280 times I. We don't know. Scroll down a bit. So I is equal to 1.2 amps. Okay, we're given the unit there. So it's just working out the transformer equation, then working out the P equals IV, that's times, that should be capital, make it clearer. What I've done there. Okay, so transformer equation, and then I've worked out power equals IV. That's actually, it's not as bad as it kind of looks, there's 2 equations there. Okay, so that's the end of transformers, so getting on to something completely different. A satellite is in a circular orbit around the Earth. Figure 14 shows the velocity of the satellite at 2 different positions in the orbit. It's orbiting the Earth, going round. Explain why the velocity of the satellite changes as it orbits the Earth. Okay, so yeah, the subtlety to do with orbits here, isn't it? So first of all, velocity is not just magnitude of speed, is it? Velocity changes as the direction changes. Number 1. Mark. Next one is the force of gravity causes the object, the satellite, artificial satellite, causes the satellite to be in what's called constant free fall. Okay, around the Earth. This means it is constantly accelerating, and therefore the velocity is changing. If all the astronauts in the International Space Station, the reason why they float is because they're in free fall constantly. Also, they have to free fall around the sun as well, couldn't you? Right, figure 15 shows how the length of a satellite orbit depends on the height of the satellite above the Earth's surface. Quite predictably, the orbit gets longer the further away it is from the Earth. It's like a bigger orbit. Okay. A satellite orbits 300 kilometers above the Earth's surface at a speed of 7.73 kilometers per second. Calculate how many complete orbits of the Earth the satellite will make in 24 hours. Right, okay, so we need to learn that for the orbit first. Okay, that's why I'm giving us a graph. So we need to go up to 300. Okay, 42,100. Let's write that down. It gives us a mark anyway. We need to write that down. Length of the orbit So one mark to reading the graph. 42,100 orbit. Okay, kilometers. It's your unit there. Right, so look at how many complete orbits we're making. We've got speed, distance, and the time. Okay, so it's the speed equals distance over time. We know speed, so it's 7.73 equals distance 42. I keep thinking it's a radius, but it's not. That's why I keep pausing like that. It's not a radius. So that time. So that means, yeah, it's auto correcting me. I thought time is equal then. Okay, so it's, if you think about rearranging that, 42,100, I'm just rearranging, not anything new here, divided by 7.73. Because it's time for one orbit. So time for one orbit, let's write that down. One orbit equals, it's that number, it's that time. So it's 5,446. Calculate it seconds. Now we need to do is to work out how many orbits it does in 24 hours. So how many orbits in 24 hours? And so we've got, obviously you convert the hours into seconds, which we're doing here. If it's 3,660 times 60, we're putting hours in seconds. And divide that by our time for one orbit, 546, and that equals 15. Our calculators. So I think there's no hard maths here, it's just remembering what we're doing. Obviously, we're checking what we're doing all the time. So, complete orbits, again, I was thinking that because that's not a complete orbit. So for our answer, we would write 15. That's not, because 8.86 is not a complete, it's like saying people. You can't 15.86 people and 15 or 16. 15 complete orbits. Okay, end our answer. This is interesting, this bit. I saw this when I first looked through the paper. Bode's law. I'm an astrophysicist, so I'm going to my planets and things. In 1772, an astronomer called J. Bode developed an equation to predict the orbital radii of the planets around the Sun. Table 3 shows Bode's predicted orbital radii and the actual radii of the planets that were known in 1772. As you can see, the only planets known were up to Saturn. Uranus and Neptune weren't known about, or Pluto and other minor planets weren't known about. The predicted data can be considered to be accurate. Give the reason why. I mean, this is just about looking at it. It sounds more scientific than it is. If you look at it, it's very close. Okay, so it's a very good law. The predicted, pretty amazing, really. Data is very close to the actual data. Yeah, think about the time, what measurements they had. Okay, that's very good. J. Bode used his equation to predict the existence of a planet with an orbital radius of 2,940 million kilometers. The planet Uranus was discovered in 1781. William Herschel, it's over there. Uranus has an orbital radius of 2,875 kilometers. Explain why the discovery of Uranus was important. Okay, so yeah, that's pretty close as well, isn't it? I think really close. Really think about the magnitude of that, the percentage, a tiny percent with error on that. My errors earlier, it's a very small percentage error. I think it's millions of kilometers. So this discovery provided evidence that supported Bode's law. prediction. It's known as Bode's law. It wasn't called Bode's law straight away. It's called Bode's law now, so I'll keep calling it that. And it works for other solar systems too. Exoplanets it works for. That's a good good approximation there. Light is usually described as a wave. Light can also be described as a stream of particles. There are two different scientific models of light. Which statement describes a scientific model? A small version of a real object. That's kind of what a model is, like a train set, isn't it? That's why it's trying to confuse people. 2, a way of guessing that will happen, or an idea used to explain observations and data. I think we know that that's the science one, don't we? So that one's the right answer there. Okay. Why do scientists have different models, like the wave and particle models of light? I mean, there's actually you could have a lot of time answering that question, like why they do. Sometimes but it's not just about light. Okay. So different models may be appropriate in different situations. So in some situations, light is measured as a wave, in some it's measured as a particle. Sometimes an old scientific model is replaced by a new model. Explain why scientists replace, I'm just going to crop this so I have a bit more room. Right, let's make myself a bit of room. Sometimes an old scientific model is replaced by a new model. Explain why scientists replace an old scientific model with a new model. There's lots of model right there, isn't there? Include an example from physics in your answer. Oh, okay, so we get an example here. Yeah, I was thinking that. I thought we were using an example of the other one, really, isn't it? So, you can have new evidence, but definitely. So, new experimental evidence or data is found. The old model cannot explain new data. Okay, so a new model is needed. So let's talk about an example. I mean, there's more than one, isn't there? An example would be the discovery, I'll go with astrophysics cosmology theme, discovery of the cosmic microwave background radiation and Hubble's data of the galaxies moving away from each other did not fit a steady state model. The new model, Big Bang Theory, is needed to explain the new data. Yeah, you could have had the plum pudding model and Rutherford's experiments, okay, as well for that one. About the oh yeah, you could have had a centric model of the solar system, replacing geocentric. Okay, you could have had a few different models there. Okay, next one. So some students use water wave in a ripple tank to model the behavior of light waves. Figure 16 shows what happens to the wave fronts as they pass the boundary between deep water and shallower water. So wave front and shallow water. Explain why refraction happens at the boundary between deep water and shallower water. Okay, you may have heard in the background an ice cream van. It's a bit cold for that, I was just laughing. Okay, so what happens? So it's shallow water and deep water. Okay, so it's going into shallow water. So actually, velocity of the wave is slower in the shallow water. So the wave front slows down. Okay, but wave fronts in the deep water do not go down, and this leads to a change of direction of the wave. I've got a different one. Figure 17 shows the wave fronts traveling parallel to the boundary between deep water and shallow water. So you can see it here. Explain why the wave fronts do not refract at the boundary. We've got a parallel one. So every point on the wave, you can answer the other one. This could help you answer the question as well, couldn't it? Every point in the wave hits the boundary at the same time. So every point slows down at the same time. Because on the other one, it didn't slow down at the same time. So this bit slowed down, so that bit, sorry, slowed down before that bit. Okay, so you've got that kind of buckling while that carries on. But this part, it didn't happen. Good. Last question, figure number 10. So in figure, the circle in figure 18 represents a straight wire, so it's different thing completely, carrying a current. The cross shows that the current is into the plane of the paper. Well, it's a wire, okay, so it's a right hand rule. Okay. So if you got your hand and you put your thumb into the paper, your right hand, put your thumb into the paper, okay, it's concentric circles. So luckily got some circles. Okay. No fill. All a few of them. This is needs to do at least 3 on my mark scheme. Yeah, I haven't got left too much room on it to draw it on. Okay, if we use the yeah, a bit bigger. It's an atom. Right, so we need to put an arrow on that too. Let's put little arrow. Let's just draw it. Okay, right, so arrow, it's going clockwise. Okay, so I'll just test my pen out. So it's going that way. So when we get, bunch up your hand, point your thumb to the paper. Okay, it's going clockwise. So next one. Oh, okay, I've done it already. Magnetic flux density 10 centimeters from the wire is 4 microtesla. Which of the following is the same as 4 microtesla? The micro to the -6, so it's this one. Okay, 4 times 10 to the -6. Okay. Figure 19 shows a simple electric motor. Carbon brush, split, it's always a tongue twister, split ring commutator, magnet, coil, axle. When there is current in the coil rotates continuously. And that's the last question of the exam, so let's finish it. Okay, so let's start writing. Get back onto this, onto typing. Right. Let's go down all the way down here. Okay, right, so let's start off. So the sides of the coil which are parallel to the magnet experience force opposite directions. Okay, so the forces cause moments that act in the same direction. One pushes it down, one pulls it up. Causing, yes, going to rotate, causing the coil to rotate. Every half turn, the two halves of the commutator swap brushes. This should have a convu. I don't think, no, I might not know that word. No, it did. Okay, so this swap of carbon brushes reverses the current in the coil to keep the coil rotating. If it didn't, it would just stuck. If it's stuck, okay. If it didn't, okay. So that's the end. So it's actually carbon brushes. So I'll tidy up my answer a bit. Typing quite fast. I'm going to tidy up brushes. Okay, so the coil rotates continuously. Yeah, because it swaps. Okay, so let's have a look what else you might have written. It's about the pair of forces, pretty much. I've got one asking what the pair of forces causes. And this is 4 marks, so it's not a 6-mark question. So this one only requires a few things, really. Okay, so thank you for listening to that. I hope you've enjoyed the videos, and I hope to see you in another one in the future. Thank you. Bye-bye.